Swayam Prabha. Digital India. Educated India.
We were just talking about this concept, so this graphic may help with it. So here's a hypothetical non-prismatic member subjected to bending moment. It's just showing bending moment here, no axial compression. It's got whatever bracing conditions, displacement, boundary conditions are coming in from the problem you're solving in general. And we need to identify a critical cross-section. And so let's say we've got something like the member that we've just been working on. And we would expect that, hey, it's probably critical at the top. Now, again, in Consteel, we're using a rule where we're basically looking at the ratio of MU to MW for all the different cross sections, and we look at whichever one is largest, right? And we're going to take that as a critical cross section, move it forward, and that does a pretty good job of capturing the one that's going to be the largest. In Design Guide 25, we would say, oh, well, you've got these various potential locations that may be critical. Please check them all. All right. So once you identify a cross-section you're going to check, let's say, oh, I think the top is most critical here. You basically say, okay, well, what's the MU to MW at that cross-section? So that's like a cross-section demand to capacity ratio, okay, or cross-section utilization if you prefer that term. Obviously, we've got to do some calculations given that cross-section to calculate MW. That's the plateau strength that we were talking about. We've also got an elastic buckling eigenvalue, gamma critical. That brings in the entire member. So you can see from what we just did, when we tapered the member, our gamma critical reduced because it wasn't as strong in terms of lateral torsional buckling. Once you have those two parameters, it can be non-prismatic or prismatic. So the way the AISC standard or other standards work, they're usually written just for prismatic members, right? And so how do we use that standard if it's a non-prismatic member? Well, we can basically set up and show that if you're checking a prismatic member, if you know MU to MW, and if you know gamma critical, you've got all the information you need to be able to calculate MU over phi MN. That's how we can check a prismatic member. What's the equivalency that we're going to use for a non-prismatic member? We go to a potentially critical cross-section. We determine the MU over MW. At that cross-section, we get a gamma critical for this non-prismatic member, and then we're not going to try to define what's the length or anything of that sort in the equivalent member. We're just going to say, okay, we want to check whatever it is, a prismatic member that has the same MU to MW and has the same gamma critical. That's how we apply the specifications, equations, to get a calculation for that cross-section. Then in general, we go to other cross-sections that might be critical, and we check those the same way. Does that make sense? And it's a very simple concept, but it works quite well. I've been asked questions before that, well, wouldn't that be conservative? You kind of maybe got something that's more local, large demand here, but the rest isn't so heavy of a demand. Wouldn't that be kind of conservative to now say, oh, I'm checking a member that's uniform? It actually works quite well. So there's a general folder. And this is the 2025 paper by White and Vasilievich. I almost said that right that time. It's for the SSRZ conference that's coming up. Let's go back to Consteel for a second. So now we've got our prismatic member, and we have both axial compression and flexure. The axial compression is constant along the length. The moment is varying from maximum at the top to 0 at the bottom. So how would we verify the strength of this prismatic member? If we look at a traditional calculation, let me get this to where you can half see it. So here's again, the 1,000 millimeter deep section. We've already done the calculations for PU and MU and got a VPN and a VMN separately. Our PU over VPN was 0.26. That kicks in the upper branch of a bilinear equation that we use for the beam column strength. Okay, we're at 1.19. That's the way we do it traditionally. Now, if you stop and think about it, it wouldn't be that hard for something like this, where it's just, oh, this is just a single isolated member that we've taken out from everything else. Okay, so now we're going to go to through a lot of extra effort to analyze this member under pure axial compression. Then we're going to go more effort to analyze it for just bending alone. Then we get those capacities, and then we can interact them. So that's the traditional approach. Obviously, if you're doing hand calculations for those things, yeah, it's easy. It's difficult to do anything else. You want to know the column capacity by hand. You want to know the beam capacity by hand. Now let's get an interaction that ties them together. But if we're using a tool like Consteel, that's extremely awkward. It's like, wait a minute. If we've got combined axial compression and flexure, why don't we analyze combined axial compression and flexure? Why are we doing them separately? So let's analyze them. We run the analysis. And so now this is a buckling load. It's buckling at 3.85 of the design load for these two loads that are applied. It's a lateral torsional buckling under combined compression and bending and an eigenvalue. All right, how do we do a design with, how can we use that in design? The general method. So now what I want to show you is basically how that works, and then we'll do a summary. This is for just the prismatic beam column. We can then look at it for the non-prismatic case. General method, okay, good. So the calculations should be starting to look rather familiar at this point. You say, boy, I think I've seen that on a previous PDF. So this is prismatic beam column verification by general method in the folder that's for Module 4, Behavior and Design of Beam Columns and Frames. So we got some section properties. That's nothing new. We got our lambda W, our A sub W. We got our CRW. That's the same calculations we were doing before. RB looks like that's a 0.833. I meant to do 3 significant figures there. That's pretty much repeated out of what we have already done. It's not that we're going to do all those previous calculations and do them again here. Let's say you're doing them for the first time here. Flange local buckling and flexure. Okay, this is the same as what we looked at before. 429 for the flange local buckling strength. Lateral torsional buckling in flexure. Okay, same lambda P, ML, lambda RLT, that's the same. Wait a minute. Right. So was it 3.85? I hope it was. Yeah, 3.85, okay. So my gamma here is a gamma from combined compression and flexure. I'm multiplying my mu by that, so I got my mu at the strength condition. Now again, here we're using the approach that precedes where we're going in the direction of always doing everything with a J, but then having to calculate a reduction factor for shear. So that 3.85, it was 4.83 when we just had bending alone. And it was 11.8, no, I think it was actually 11.97 when we had axial compression alone. I think that was an earlier thing, and I changed a little. All right, so we're not quite done. We need to basically also get our, we need to get our given our M criticals, given our also our load, corresponding to critical load, we need to figure out the demand to capacity ratio under combined compression and bending. So to go there, here's where I'm bringing in, okay, I've got a yield moment. I need to calculate a yield axial load. Py is Fy times the gross area. Okay, so we're going to get a gross cross-section demand to capacity ratio. Basically, this is a yield equation, right? This is increased from 0.69 for flexure because we've added axial compression. It's increased from 0.0658 for axial compression due to the fact we've also got bending. Now we calculate an out-of-plane non-dimensional slenderness using our elastic buckling eigenvalue, gamma critical OP, for the out-of-plane buckling, and our demand to capacity ratio for the gross cross-section. So I've shown you that form of it earlier. We need to use it in this form now to cover the bases with the combined loading. We got 0.586. So now that slenderness is used in both the flexure calculations for lateral torsional buckling and the column strength equation for the column axial compression. So when I go to the LTB strength, I've got a lambda critical OP here where we had lambda LT before. So that's 432 now, where it was 441 when I had flexure alone. The ratio to MY, 0.74, if I just look at it as moment to MY. Here's my FEMN is the minimum of these. Now I thought I had, yeah, and I've got, I think, oh, this one's prismatic, so I didn't need to do that. Let's go to non-prismatic. Well, no, we still could have checked. Still could have shown you where we are with respect to flange local buckling. So if I scroll up here, flange local buckling to MY was 0.734. And now we've got a lateral torsional buckling strength. That's okay, it's 0.74. So flange local buckling is still just barely controlling for this prismatic case. All right, so that's the flexure. Now we've worked the column strength calculations. Again, we get a P critical out of plane by multiplying the eigenvalue by our PU. So now this is the axial load at elastic buckling. We get a, we've already got our lambda critical out of plane. We did that above here when we were doing the check here based on this cross-section demand to capacity ratio that incorporates axial and bending. Okay, so we carry that into the column strength equation. And so now we get an Fn, then we use our Fn to calculate our effective widths, and we get an effective area. We get our column capacity. It's now 744. It was 584. Okay. And then we now can take our phi-min and our phi-pn that we've just calculated. The Pu over phi-pn is larger than 0.2, so this form of the bilinear equation applies. We get 1.13 versus the traditional check is 1.19. Now in the traditional check, we usually take the demand to capacity ratio Pu to phi-pn, and if you go back and look at what we did, it was at the very bottom of the section. Could say. And now we say, oh, but the moment is up at the top. Do we think those are that closely related? And so that's a loose argument for actually the general method is giving you a better representation, and it's allowing you to take advantage of various attributes where with a tool like Consteel you can capture various continuity effects in the structure and various complexities of the geometry. Now in terms of the cross-section check here, again it would be an MW for the flexure and a PNS for the PNS is based on the effective area that we get using an FY basis for effective widths. And so in Consteel, the calculation is looking for basically calculating this for all the cross sections throughout the structure, and then identifying where is the cross section demand to capacity ratio the largest for a given member. We go there to then do the member calculations. So that's prismatic. And I think maybe before we look at the non-prismatic, it may be good to basically walk you through what we just did, but more in a presentation form of the steps. Step one is generally we're going to perform an in-plane geometric nonlinear second-order elastic structural analysis with imperfections or equivalent notional lateral loads. Now, per AISC 360, they say, okay, that means use the direct analysis method rules for analysis model. And so the mantra there is a 0.8 stiffness reduction on all elastic stiffness contributions, and if it's a frame, out of plumbness of 1 in 500. That's the erection tolerant, maximum erection tolerance on out of plumbness in a frame. And if we get into some other things, we might need to talk about out of straightness and so forth. Per Eurocode, it's nominal elastic stiffness. We increase the magnitude of the imperfections to account for the same things that in the US we're trying to account for via a stiffness reduction. So again, you've heard me say this before, these methods are really a poor person's test simulation. You're basically saying, hey, I want to be able to do something that's in a design setting that's practical for a design office use, but I want to get at least a coarse estimate of what's really going on in the frame. Because I know if I do an analysis of the structure, nominally elastic, perfect geometry, that's not really giving me the internal moments and so forth that are actually occurring in the structure, particularly if I'm getting significant stability effects. And so this approach is aiming to try to at least get a coarse calculation of what are those real forces. So once we have step one accomplished, we move to step two. And so with the way that it is implemented in Consteel is we determine a cross-section demand to capacity ratios throughout the structure. And we identify, the designer identifies, okay, I want to call this a member, this a member, this a member. And then we look at, well, where is the largest DCRCS, so that's based on PNS and MW. PNS is based on effective width based on FY. Okay, same as in Eurocode. So we identify a critical cross-section based on that, and we say, okay, we've got our critical cross-section now. We're going to do the check, our member check, just on that cross-section. Whereas Design Guide 25 would say, oh, you may have these 4 or 5 cross-sections that are critical. Please check them all for the member. Now, in the calculation of the non-dimensional slenderness of the member, we need a gross cross-section DCR, so that's the bottom here, DCR CG, for G for gross. So that's step 2. Step 3, we determine our elastic buckling load ratios for out of plane. And so generally different buckling modes are applicable for different portions of the structure. And so Balint is going to discuss that in a subsequent lecture, how we deal with that. Then step 4, we calculate the applicable member out of plane non-dimensional slenderness values. So I've got 1 lambda OP, or lambda critical OP, I think is what I called it before, right? Square root 1 over lambda gamma critical OP over my DCR for the gross cross section. So given that, that gets entered to the PHN equations and to the PHMN equations, and we get axial compressive and flexural strengths. And now we're ready to wrap it up. We calculate the member demand to capacity ratios, and per AISC, we use this bilinear strength interaction equation. I can tell you that in the bridge standard in the US, with what we developed there with fairly major updates for handling big box sections and all kinds of things, quite honestly, the bilinear equation in AIC 360 is a bit of a cheat when it gets to some of these cross sections that have very thin webs. The better interaction equation is really just the linear interaction equation for that, and that we're pointing that out in the paper that I was showing you the figure from there here at the start of this session. And it's pointed out in the bridge standard that, look, if you've got a slender web, you should use the linear interaction equation. It's not a big difference one way or the other, and so there's a lot of these things where it's easier to just, okay, fine, just keep cheating. It doesn't change it that much, and because I can't have another argument with you about it. Okay, all right, so that's it. That's how the general method works. So let's go back, and let's look at the non-prismatic beam column. Now, traditionally, and in Design Guide 25, we would say, okay, carve out that member, and let's do a special analysis. Oh, you got to build a whole special model for this, loaded in concentric axial compression. I had a good question during the break. Wait a minute, if you in some of these cases non-prismatic, don't you put axial force on it and you get some bending because of the non-prismatic geometry? If you've got steps or transitions and so forth, you can't actually put axial compression on it without causing some bending. It's somewhere along the length. So that's kind of ends up being a huge headache. Then we kind of contorted ourselves all sorts of ways to address that question in Design Guide 25. So if you put on these notional loads and then you can take that bending out and now you've got pure axial compression, and oh my God. With If we've got something like what we were looking at here, it's just a nice linear taper, okay, yeah, there's still no bending that's introduced when we put axial compression on it. So we can get an axial compressive resistance. We already got that earlier. We can get a flexural resistance, and then we put it together, right? So we basically separate calculations. What's the member's strength under pure axial compression? What's the strength if we don't have any axial compression and we just have the bending part? All right, so that's the traditional calc. If we want to drink the Kool-Aid with the general method, so again, there's a lot of things that are going to look very similar here, right? So maybe if we repeat this enough times, then you've got it memorized. At least this column you can do. Right. And then we're going to change it and say, okay, how can we make this? How can we handle this frame handle a higher wind load, and how can we address the fact that it didn't quite work before, and make it lighter, or less, or more cost effective. Okay, so we've got, you can see yielding and local buckling and flexure. We got our RB showing up there again, our MYC, our MW. Okay, we got our plateau strength. We do our flange local buckling check in flexure. That's a repeat of what we had before. Okay, lateral torsional buckling. Again, lambda PLT is 0.35 since it's a slender web. It's always a constant. We got our ML, our lambda RLT, that's square root of 2. ML is half of yield moment. Oh, but wait a minute. We go back over here. Here's the column in consteel. Again, I've got a lateral load and a vertical load here to give me the correct vector component along the centroidal axis at the top. And then our applied moment will come in. We'll analyze this case. We'll get our buckling solution. So there's what the cross sections are doing in terms of the lateral torsional buckling. But it buckled at 2.85. That's lower because of the combination of axial compression and flexure. You can see that we're getting still fairly significant action in the top unbraced length. That's where the moment is highest. And remember, these metal building frames, they're typically just glorified beams. They're dominant flexure. And what are we doing with the non-prismatic geometry? We're basically following the moment envelope and getting a more efficient design by following the moment envelope, right? But they've got some significant axial compression in them that we can't ignore. So we've got to deal with that. Okay, so we got 2.85 coming out of consteel for this combined loading case. So there we have it. We're introducing that into the calculations here. So our moment at that buckling load is gamma critical times mu. Again, everything here is done with j equals 0. So 2.85 was reduced from 3.47 from bending alone, or from 12.0 from axial compression alone. So now, again, we do our gross cross-section demand to capacity ratio. That's 0.756. That's increased from 0.69 for flexure and from 0.0658 for axial compression. We calculate our non-dimensional slenderness for the out-of-plane buckling. And now we're ready to calculate our moment resistance, where we're using the non-dimensional slenderness that accounts for the combined loading effects. So we got 411. It was 419 when we did flexure alone. So here I think I missed it in the other file, but here you can see, so now finally the lateral torsional buckling has been weakened enough so that flange local buckling is not controlling now. The lateral torsional buckling is the controlling limit state now on this tapered member. And so 0.9 M in LTB is 370. And we need to do the strength calculation for the axial part. So again, we bring our gamma critical out of plane in to calculate what's the axial force at that out of plane buckling. We've already calculated our gamma critical out of plane, so we plug that into the column strength formula. We get 284 megapascals for the stress. And then by the approach in AISC, we're saying, hey, if this column is long enough, maybe I start a lot of my plates that are very thin are more and more effective. So we check, yeah, that really, really thin web is still not going to work as being fully effective. So we need to calculate the elastic buckling stress for the web, get a web effective width. And so still only about 25% of the web is effective here for our strength calculation. The flanges, also the flange BF over 2TF is larger than this check, so we've still got some reduction we need to take for the flange. So we're losing about 12% of the flanges in terms of their effectiveness because of local buckling and the post-buckling action of the flanges. We add up all our effective areas, and so again, this cross-section here at the top of this it's one of the most severe in terms of really pushing the limits of local buckling and slenderness of both the flange and the web of any that I've encountered. But this is pretty much the cross section out of the this particular frame from Professor Lee and Ketter and Su's design in this Metal Building Manufacturing Association book from 1981. All right, so the column capacity term ends up being 721. It was 585 for axial compression alone. We do the demand capacity ratio. We get 1.18, so 0.03 smaller than the traditional check. Again, the traditional check, the axial was critical at the bottom. The moment was critical at the top. Really? Do we really need to combine those? Well, we always say, I don't know how many software providers I've told, yes, that's the way you're supposed to do it. And then all the software providers go cross-section by cross-section by cross-section by cross-section and just look at what's going on for each one. You know, you could say we're doing cross-section by cross-section things here, but we're doing it correctly. A lot of the calculations out there really don't have a basis. And then I'm just showing the cross-section checks at the end here, where in Consteel, the cross-section demand to capacity ratios are used to identify, okay, it's not perfect, but it's generally pretty close. If we go to that cross-section, we've got that where the cross-section demand to capacity ratio is greatest. We then treat that one cross-section to evaluate the member strength for the member we're considering. That's sufficient. We're done. Probably the hardest thing once we get to these, now obviously you can have it programmed in Consteel, and Consteel takes out the drudgery, or you have worksheets in the design office, and you run it through many times through your worksheets with all these different checks that you have to do. But hey, if it's a non-prismatic design, you've got more checks to make. But you can say the same. You can say the same thing if hey, it's a big structure. I've got 1,000 columns. Does that mean I only can check 500 of them? No, I have to check each one and make sure it works, right? So you got more cross sections to check when you've got non-prismatic columns. Okay, so that I think that gets us to the point where we're essentially in our day 7, but we're going to take advantage of the fact that we're kind of a little bit ahead of the game, and the idea is to try to get you started on grouping together and seeing and trying to see, okay, how can we make this particular design better? Before we get there, I think we need to understand, well, how do we model this frame? So that's what Balint is going to spend some time doing now.